In this module, we will take a look at some more functional forms used in the classical linear regression model. In economics, one very important area is the area of cost and production. Here, we typically have non-linear relationships between variables. We will take a look at some such non-linear relationships and we will make adjustments so that we can incorporate these relationships in the framework of the classical linear regression model. We begin with the concept of average variable cost. So, average variable cost AVC or average cost is defined as total cost by output, and a typical average cost curve is U-shaped. So, this equation would be a quadratic equation. Question is, how do we adjust this in order to make it amenable to the classical linear regression model? So, what we write is, in general, yi is equal to beta 1 plus beta 2 xi plus beta 3 xi squared plus ui. We denote output as x and average cost as y. So, the average cost is a quadratic equation in output, and obviously it is not linear in y and x, but we can just rewrite this x as x2i, and we can rewrite this xi square as another variable x3i. So, now the model becomes yi is equal to beta 1 plus beta 2 x2i plus beta 3 x3i, where x2i is the output and x3i is the square of the output of the ith observation. Together with this, we also add the random disturbance term ui, and a very well estimated model would look like this, where the dots represent the scatter of average cost against output, and as you can see, it is a non-linear relationship, but we have been able to estimate it using the classical linear regression model. In a similar way, the marginal cost MC, which is the change in total cost due to change in output, is also captured by the same kind of model. So, the shapes of the average cost and marginal cost are similar. Their positions differ, but their shapes are similar. And so, we can also capture this marginal cost with the help of the same model. Obviously, the data will be different and the estimates will also be different, but the format of the model remains the same. Once again, the estimate will be yi hat equal to beta 1 hat plus beta 2 hat x2i plus beta 3 hat x3i, and then we can obtain the standard errors, we can obtain the t values, and we can test hypothesis h naught against hypothesis h1. Maybe this hypothesis is beta 2 hat is equal to 0 against beta 2 hat, not beta 2 hat, beta 2 equal to 0 against beta 2 not equal to 0, or some similar composite hypothesis. Next, we will take a look at a cubic function which will be used to estimate the total cost function. Now we take a look at the total cost function or the total cost curve. Typically, a short run total cost curve measures the relationship between total cost, we call this y here, and output x. That also is a non-linear relation. So, it is clear this is a cubic function. So, in economic theory we say total cost y or total cost y is equal to beta 1 plus beta 2 x2 plus beta 3 x3 plus beta 4 x4 sorry xi square xi cube. So, output is x, the square of output is x square, cube of output is x cube, and the total cost is a cubic function in output. Total cost is a cubic function in output. So, we rewrite it as yi equal to beta 1 plus beta 2 x 2i. We are just renaming xi as x 2i. This is one variable, the output. The next regressor is beta 3 x 3i. That means xi square is now denoted as a new variable x 3i plus beta 4 x 4i plus ui. So, output x 2, output square x 3, output cube x 4. So, this model is now linear in beta 1, beta 2, beta 3 and beta 4, and we can simply use the ordinary least square estimates. That will give us the estimate of this total cost function. All of these, the total cost, average cost and marginal cost, they actually emanate from what we call the production function. So, this production function gives rise to cost equations or cost curves. For example, we had average cost, marginal cost, total cost. So, how does the production function look like? The production function typically shows the relation between output and input. So, if there are more than one inputs, then one way to handle it is to show one input explicitly and keep the other inputs implicit, or to keep them fixed. And the production function that we have goes like that. So, initially the production function shows that output rises faster and faster with input. That means productivity is increasing. Gradually output rises slower and slower, that means productivity is decreasing. But in empirical analysis, oftentimes we come across production function that shows relation between output and input such a way that the incremental output is always decreasing. So, this is another nonlinear relation in input and output production function, but it is not a standard neoclassical production function. It shows continuously increasing output, but the rate of increase gradually decreases. We will take a look at one example which can be used to estimate this kind of a production function. let us see how we can use the multiple linear regression model or a simplified form of that to accommodate a nonlinear equation that shows production function with decreasing productivity. So, this example is taken from fishing. So, the catch that one gets is modeled by a regression beta 1 times effort minus beta 2 times effort square plus u. So, the ith observation of the catch is explained by ith observation of the effort, ith observation of the square of the effort and ui. Needless to say, by now all students will have understood that this is like saying yi is equal to beta 1 x 1 I plus beta 2 x 2 I plus ui. Only difference is here we are writing in a general form plus beta 2, that means this beta 2 has to be negative in order to get the diminishing productivity picture. So, that is why here beta 2 is positive with a minus sign in front, here this beta 2 is negative. This is the general form where this beta 2 is negative and the particular application shows beta 2 to be positive, but with a minus sign in front. So, that is your catch and that is your effort. This shows that with an increase in effort, catch rises, the amount of fish caught rises, but the incremental catch gradually decreases as effort increases. That is a typical portrayal in the fishing industry. An example is provided in the study material. Do go through it because it contains more information on the standard error, the t values, r square, so on and so forth, which will help you to assimilate the estimation of this type of a model. After this, we will take a look at another form which is called the reciprocal form. Viewers, as already mentioned, we have to take a look at the reciprocal form, but before that let us once again visit the example of the fishing industry that we have taken. So, the regression looked something like this, that is catch was equal to beta 1 effort minus beta 2 effort square plus u with subscript I. You will have noticed something interesting about this regression. This is yi equal to beta 1 x1I plus beta 2 x2I plus ui. Here beta 2 is negative, here beta 2 is positive. The interesting thing is that this regression is a regression without any intercept. So, x1 is not the intercept, it is a variable effort, and this will have different values, unlike the standard format where we had y regressed on x2, x3, x4 up to xk and x1 was the intercept. Here x1 itself is a variable and there are two variables x1 and x2. So, this is a model without intercept, but we do not have any reason to worry. This also follows the standard format y equal to x beta plus u. So, where y has n rows and 1 columns, x again has n rows and k columns, beta has k rows and 1 column, and u is n cross 1. So, that is the matrix formulation, the generalized matrix formulation of a model even without an intercept. Only difference is this model will be estimated with beta hat as x prime x inverse x prime y as explained earlier. Only thing is we cannot use the model in deviation form. When the model has an intercept, then we can estimate the slopes by considering the data in deviation form. Here, because it does not have any intercept, we have to go by capital X and capital Y. We cannot use the model in deviation form. So, x prime x inverse x prime y giving b hat, that is beta 2, beta 3 up to beta k, that is no longer applicable. This part is no longer applicable. So, we can use the same techniques, ordinary least squares estimate, but we cannot use the model in deviation form. Another interesting thing about this is, now we write y is equal to y hat plus e. That is basically observed is equal to estimated plus error, and y prime y is equal to y hat prime y hat plus e prime e plus twice y hat prime e as earlier. Only thing is y hat is now x beta hat. So, x beta hat means y hat prime is beta hat prime x prime. So, if you substitute here, then what do we get is y prime hat y hat plus e prime e plus twice, instead of y hat prime what we write is beta hat prime x prime e, but that x prime e is equal to 0. If you recall earlier modules, that is basically the matrix formulation of the normal equations. These normal equations are represented in matrix form as x prime e. So, once again we have y square y prime y is y hat square y hat prime y hat plus e prime e, and this we now term as total sum of squares is equal to explained sum of squares plus residual sum of squares. So, the same decomposition of the total sum of squares still applies. Only thing is, earlier we had the small y because we could use the model in deviation form. Now, because the model does not have any intercept, we cannot go for the deviation form, but we can still partition the total sum of squares into explained and residual sum of squares using capital Y and capital E. Now, we will go to the model in reciprocal form, which will also show us an interesting example of economic application. Let us now consider a regression which is known as reciprocal form. So, let us take a concrete example from economics. Let us talk about child mortality. We know that as a country develops, as an economy develops, child mortality should fall. So, if we denote child mortality by the variable y, then this child mortality should be declining as the economy develops. One variable to show the development of an economy is per capita GNP. So, say that is y, sorry, that is x. So, we would expect to get a relation like, if you have here child mortality CM and this is per capita GNP, then we would expect a relation like that, where with an increase in per capita GNP, child mortality decreases, but it can never reach 0. So, child mortality kind of asymptotes to a particular value. So, reciprocal form is used when the y variable asymptotes to some particular value. In this particular case, we can write yi is equal to beta 1 plus beta 2 into 1 upon x 2I. Just to maintain symmetry, I am denoting this x as x2, the same thing. You could have written xi, but just because we have beta 2, I am writing x2. So, beta 1 plus beta 2 x2I plus ui. And here in this example, beta 1 and beta 2 are both positive. So, as you can see, as the value of x2 becomes very large, this component will become very small. So, y will asymptote towards beta 1, and if beta 2 is positive, that means greater the value of x2I, smaller is the value of yi. Higher x2, smaller y. Higher per capita GNP, lower is the child mortality. So, this is a very nice example of a reciprocal model or model in reciprocal form. Now, it is not always necessary that both beta 1 and beta 2 be positive. So, another case you could have is where beta 1 is positive, sorry, beta 2 is positive, but beta 1 is negative. So, in case of reciprocal models, it may so happen that the coefficient beta 1 is negative and the coefficient beta 2 is positive as earlier. In that case, the graph showing the relation between y and x would be something like this, where y asymptotes to beta 1, but beta 1 is now negative. So, here we have beta 2 positive, but beta 1 negative. Another possibility is where we have beta 2 to be negative. So, this is y and x, and if beta 2 itself is negative, then the relation asymptotes to beta 1, which is positive, but the graph looks a bit different. So, these are two other examples of reciprocal model. And the earlier one that we have already considered was the example of child mortality with per capita GNP. So, this is the case where both beta 1 and beta 2 were positive. If beta 1 is negative, but beta 2 is positive, then this is the kind of graph that we get, whereas if beta 2 itself is negative, then that is the third example that we get. So, before concluding this model, we now take a look at logarithmic reciprocal model. That is a model which can capture the neoclassical production function, which initially has increasing productivity and later on has decreasing productivity. So, we quickly recall the shape of the short run production function in the neoclassical model. As we earlier saw, the relation between input and output in the neoclassical production function is a nonlinear relation. So, there is a point of inflection. Before that we have increasing productivity, after that we have diminishing productivity. So, the model that captures this kind of behavior is log yi equal to beta 1 plus beta 2 1 upon x 2I plus ui. Once again, the relation is nonlinear, but the model is linear in beta 1 and beta 2. So, that, dear students, brings us to the end of the different main functional forms, and please go through the study material where these are discussed in more details. Estimates are given, T ratios are given, confidence intervals are given. So, that helps you to recap the whole process of estimation, testing of hypothesis in the context of not the standard simple format where y is regressed on x, but also in the context of non-linear regressions which are non-linear relationships which are accommodated within the framework of the classical linear regression model. Please remember, whatever we are doing is a linear regression model, and the linear regression model can accommodate non-linear relationships. So, we now end this module and hope that you find the study material enriching. Thank you.